So this is the last example in section 1.8, and it's a story problem. So you know it's going to be an interesting one, right? We're going to see how what we've learned how to do applies in context. So in the example, it says a person initially places $1,000 in a savings account that pays interest at the rate of 1.1% per year. Now notice, percent is not actually a unit. It's just a way of rewriting a decimal, right? But the per year is definitely a unit. And then it says compounded continuously. So there's some information already in here that we need to pay attention to. So the idea that it's compounded continuously means that we should expect exponential growth, right? And then it says, suppose that the person arranges for $20 per week to be deposited into the account. I don't know if any of you have a savings account where you deposit money on a regular basis, but it's a really good strategy to kind of force yourself to automatically deposit a certain amount per week or per paycheck into the account. You just don't even think about it. So notice part A says write a differential equation for P of t, the amount after t years, the amount in the account. And it says assume that weekly is essentially continuous for the purposes of modeling. Now notice, because t is in years, so weekly is like 1/52nd of a year, right? So weekly is as close to continuous as we need to be. So for part A, we need to write our differential equation, which is going to be dp dt, the rate of change of the amount in the account per year, and that's got to be equal to some growth from the interest plus, and there's no decay in this case, we're not taking out anything, plus the growth from the deposits. So I'm going to make a little note and say there's no decay since there's no withdrawal. Right? If you start withdrawing from the account, then it gets a little bit more complicated. We'll get there. We're just not there yet. So we have this dp dt equals growth from interest plus the growth from the deposits. Now what I want to do real quick before we get too far into this is take a look at the units. Because as is usually the case, the units have to tell us what's going on, and we have to obey the units. Over on this side, whatever the units are for this, that has to be the same units for each one of these. So P is just going to be the amount of money, and T is years. So it's amount of money per year. That's got to be the unit for each one of these terms. It's got to be dollars per year and dollars per year for this one. So whatever we come up with to place in for growth from interest and growth from deposits, from deposition if you want to think of it that way, then that's got to have the same units. So dp dt is equal to the growth from interest. Now keep in mind you might be tempted to just throw in exponential growth and go like P0 e to the, but this is the rate equation. This isn't telling me how much money. It's telling me how much money am I gaining per year. And that's where this rate right here becomes super important because it's going to be 0.011 times P. Now, why the 0.011? Because this has units of dollars, or not dollars, darn it. It has units of per year, right? That's all that it has for a unit. And this has units of dollars. So multiply them together and you get dollars per year. The other term, the growth from deposits, well, what do we know she's doing? Well, she's dropping in $20 per week. So we can write that and say $20 per week, but it's dollars per week. Now, dollars per week is not the same thing as dollars per year, so what do I have to do? What do I have to multiply this by? Well, I'd have to multiply dollars per week times the number of weeks per year. And so those of you who are quick with a calendar know that there's 52 weeks per year. And sure enough, if we do the unit cancellation, we wind up with dollars per year and dollars per year. So that means that my differential equation, the end of part A, is just dp dt equals 0.011 p plus 20 times 52 is 1040. So there's one other piece of information that we're given in the problem that we didn't use. We used the $20 per week. We used that compounded continuously. What about this? What about the $1,000? What's that useful for? Why did they give us this? Well, the key is right here initially, because it turns out that we know P of 0 is equal to 1,000. We know an initial condition, right? And of course, we can't make predictions without an initial condition, because we have a differential equation and an initial condition. And that allows us to solve it to get a particular solution and then make predictions. So now part B says, okay, find the amount on deposit after 5 years. So for part B, we're actually going to have to do some solving here. We're going to solve the IVP and predict what is the amount in the account after 5 years. So let's do that. Now notice, we have a problem that we already know how to solve. This is a differential equation in terms of P. There's no function of T over here. So we could, if we want to, take this whole thing and move it, divide by it on the other side, multiply by dt. We could do separation of variables on this, but I'm actually going to treat it like it's a problem from this chapter, and we're going to find y sub h. And so we kind of take that first chunk of it and find y sub h, and you can hopefully see that, not, in this case, it's not y sub h, it's p sub h. Sorry. Because we're talking in terms of p. So p sub h in this case is the solution to that differential equation, right? Forgetting the extra term there, which is pretty easy to find. That's just a constant times e to the 0.0011 p power. No, p, t power. Man, I'm making mistakes all over the place. T power upstairs. Now I need to find a particularly lucky guess. And it turns out that my p with a little subscript p, my particular solution, once I manipulate this thing, move the p term to the other side, I have dp dt minus 0.011p equals the number 1040. Now, normally we get to this point and we'd be like, okay, what kind of function can I plug in for p that when I take its derivative and add or subtract 0.011 times itself, I get a constant? Well, it turns out the guess in this case is just a constant. So off to the side, I'm going to say, we're going to guess, here I'll use a different color, we're going to guess p equals just a constant, p with a little subscript p, equals just a constant alpha. And that means the derivative is equal to 0, which makes my life a whole lot easier. That means I have 0 minus 0.011 times alpha equals 1040. Pretty easy to solve. You find out that, oops, I'm not going to do it in green. I'm going to say alpha is equal to whatever 1040 divided by negative 0.011 is. Right? It's just a number. But this now gives me my general solution. My general, there I go writing a y again. I'm so used to writing y's. My general solution for this is going to be P of t equals my homogeneous solution, C e to the 0.011t, plus my general or my particular solution, which is just alpha, which is just minus 1040 over 0.011. And again, I'm not going to figure out what that number is until I'm all done and I'm ready to throw in some values. So I can, now that I've combined it, I'm actually going to use my initial condition. So let me grab my red marker here and say let's use the IC to solve the IVP. And that means P of 0 equals 1,000. And that's got to be equal to all this stuff over here when I plug in t equals 0. So t equals 0 makes this thing just be 1. So it'd be C minus 1040 over negative, not negative, 0.011. So I want to solve this thing for C, add that to both sides, and I wind up with C equals whatever 1,000 plus 1040 over 0.011 is. Right? It's just a number. I'll let the calculator figure it out in the end. But for right now, I'm just going to drag it around with me. Very last step, I'm going to use my particular solution now, and I'm going to make my prediction. So I can predict the amount that she's going to have in the account after 5 years by subbing in 5 into my solution, into my now particular solution. So that's going to be approximately equal to what? Well, when I sub it in, I go through the steps, and I get something that looks kind of like 6,402.19, and of course these are dollars, so I only need 2 decimal places. So this is after no rounding up to it. I just throw the numbers in afterwards. Now, we could, if we want to, step back and say, if I need to solve this differential equation, solve this IVP, I could have treated this like a separable differential equation and done it that way, and you'd get the exact same answer. Notice the end result right here is exactly what you would get if you did divide both sides by all of that and then integrate. It's going to involve a natural log and some other stuff in there, but you get the same result. I personally think this method goes a little bit faster. And of course, when all is said and done, we can hop on Maple to check the answer there. So switching over to Maple here, boop, we can see that we can solve our differential equation and include the initial condition to do a desolve of the IVP all at once. And notice Maple gives it to us with that denominator not as a decimal, right? It doesn't like carrying around the decimal. But it's 100% accurate. And at the end, if I substitute in 5 for t and ask it to evaluate it out to, I don't know, 10 digits, we see that our answer appears. Right? We can evaluate at a particular point to figure out what the value is. And so sure enough, it worked out. And so our solution that we came up with, doing it by hand, is verified with Maple. So the nice thing about the process here is this whole problem kind of ties together a lot of stuff that we've been doing in Chapter 1. Coming up with a model, checking units, making sure that when we write things out, the units match up for each term. And then we have an IVP, recognizing the initial condition. And now we have a fancy method for solving it, but we could have used a separation of variables method as well. And after all is said and done, we can use the initial condition to solve the initial value problem, come up with a model and make a prediction. Now, we could predict how much is she going to have after 10 years or 20 years, but it's worth noting that after 5 years, that $1,000 is now $6,000. But consider the fact that she's dropping into her account $1,040 every year just in the $20 deposits, right? This is the deposit per the weekly deposits. So every year she's dropping in over $1,000. That means that after 5 years, she's already put in $5,200 in deposits. So when you look at this and you think, wow, 5,200 of this is in just in the weekly deposits. That means 1,200 is coming from the growth due to the interest. And remember, she already deposited $1,000 to begin with. So really only about $200 is coming from the interest rate. So it doesn't seem like she's earning all that huge of an interest, and she's not, but it's that weekly deposition, it's that weekly deposit into the account that's making a huge difference. And as the differential equation suggests, the weekly deposits continue to add to the value of P, which then gets multiplied by this growth rate, the exponential growth rate for the interest rate for the account. So the more money you have, the more money you make, which is pretty standard process in banking. So that gets us to the end of section 1.8.